Good morning, everyone. My name is Ricardo Barros, and I'll be talking to you today about decision-making systems in game AI. This talk will be engine agnostic, but if you're interested to learn more about specifically Unreal Engine, there will be a State of AI in Unreal talk tomorrow. So I've joined the Sumo Nauticum studio about a year ago. I've been in industry working in AAA for 7 years now, where I've worked as an AI programmer, and I'm really passionate about developing technology for NPCs in video games, which is why I'm really happy to be here today talking to you about this. Before we get to the core of our talk, I wanted to first give a little bit of context by talking about the Sense Think Act model. This is the basis for a lot of the AI systems in video games nowadays, where this is a three-layer architecture where the sense layer is in charge of perceiving the world around the NPC, the think layer is in charge of rationalizing that information so that the NPC can make a decision about what it should do, and then the act layer will actually enact what the think layer derived it should do. So the sense layer. When we're designing NPCs, we purposely restrict the amount of information that they can perceive the world around them. This is not only to allow us to make them look more realistic, but also to allow us to tune the gameplay experience so that it's a little bit more fun. Because it wouldn't be fun if the NPC knew everything around the world, about the world at all times. Now, a common solution to restrict information is to make use of senses and stimuli, where stimuli are events that are perceived by the NPC, and these can be things, they can be visual stimuli, so things that the NPC can see, or that we model that they can see, or auditory stimuli, things that the NPC should be able to hear. And to capture these stimuli, we have to build senses. Now, for vision sense, a very common solution is to implement vision cones. So anything that would fall inside of the vision cone, the NPC would be able to visually see it if it's within its line of sight. And then we can go from there and execute whatever action we need it to be. Now, there's other senses you can implement as well. You can go crazy and model whatever simulation of senses you want, but vision hearing would be usually your first to implement. Now, the think layer, this will be the core of our talk, which will go in more depth in the slides ahead. But the focus of this is essentially to interpret the information and to reason about change that happens in the world. And you will do that so that you can decide what should I do about that information. So if the NPC perceives the player, what should it do once it perceives that player? And finally, the act layer is in charge of actually enacting whatever the previous layer decided it should do. So as an example, say that the NPC needs to navigate from point A to point B, then the act layer, the locomotion system of the act layer, will actually be in charge of navigating the NPC from point A to point B. Okay, so moving on to the think layer. And in this talk, we will particularly be covering four different architectures, and that is state machines, behavior trees, action planners, and utility systems. There are other architectures that you can implement in video games, but these are the four that we'll talk today. And we'll start off with state machines, particularly finite state machines. Now, chances are you're very familiar with these already because they're incredibly common to be used in video games. They're used in UI flows and animation graphs, but they can also be used for decision-making systems with our NPCs. We'll also talk about hierarchical finite state machines, which is a variation on the finite state machine that looks to solve some of its scalability issues that we'll cover in a few slides. Okay, so finite state machines, what are they? So at its core, finite state machines are defined by states and transitions. We have a very simple example here where we have a state A and state B, and they will transition between each other given a certain condition on event. Now, a state, in this case, it can be a behavior, it can be a piece of data, it can define how an NPC is at a particular point in time. And the transitions will define how we transition from one state to the other, usually via some conditional information or some triggers that might happen around the environment. So when implementing your state, you will need to update your state. For example, if you have a go-to state, you will want to be updating it until the NPC reaches its destination, for example. when you first enter a state, you will want to initialize any data that you might have, and you might also want to implement a non-exit state where you can do some bit of cleanup. This is just a very common, simple interface that you can implement to your state as an example. So, covering a very simple example with 3 states. We have a patrol state, an attack state, and an investigate state. We have set up some transitions between these states. Worth noting that these are oversimplified conditional transitions. These transitions would be a lot more complicated in the real scenarios, such as the state machine would be. But for the sake of this talk, so to make it simpler, we're going to have very, very simple conditions between our states. So as you can see here, you have these 3 states. They can go from attack to investigate if the enemy is lost. If the enemy is patrolling and he heard a noise, he might go investigate, etc. Now, what we're going to do next is we're going to add a new state, the runaway state. We want the NPC to run away if it feels like it's in danger. But as we can see, we're starting to run into one of the issues with state machines. It suddenly became a lot more complicated. Having a look at them side to side, we can see that just adding a simple state suddenly meant that we had to go back to all previous states and think, okay, what state makes sense to transition into this new runaway state? And by doing so, we've exponentially increased the amount of work we have to do, because we have to go back to every single state and see if they need transition to this new state. So yeah, with the new state machine, we now have 12 possible transitions just by adding a 4th state. So, what are the advantages of finite state machines? They are very simple to implement, visualize, and conceptualize, as in, because they are so visual, it's quite easy to follow the logic following from one state to the other. They're quite efficient transitioning between state to state. It's what state machines are meant to do, so they are quite good at it. And depending on their size, they can be quite easy to debug. Obviously, the bigger they become, the harder it becomes to follow. So smaller state machines, easy to debug. Bigger ones, not so much. Some points to consider: they scale very poorly with the number of states, as we saw in our very simple example of just by adding 1 state, we've added so many more possible transitions. And by default, it loses state history. So if you want to keep track of what the NPC was doing a few frames ago, or a few seconds ago, or a few minutes ago, that's information that you're going to have to store. It's a little bit more data that you're going to have to write. So it doesn't give you this by default, but it's not hard to add either. And what games use it? Well, almost every single video game out there uses it one way or another. It is a very common and easy pattern to implement. And as I said, you can use it in UI flows and animation graphs. But here's a couple of examples of games that actually use it for decision making for their NPCs. Okay. So next, we're going to cover hierarchical finite state machines. These look to solve some of the scalability issues of finite state machines by providing a high-level state machine. So what we're doing here is aggregating states, aggregating multiple states into a state machine, and having a high-level state for that state machine. So an example here, we've created a new state machine with 3 states: shoot, move to cover, and take cover, and we've aggregated all of that into a single cover combat state. And that means we can then transition between these states with a higher level state machine. Now, these share a lot of the same advantages as finite state machines, such as being able to very easily transition between these states, but they can also run into scalability issues if these become quite complex, and now you have to also deal with a new layer, and there's nothing stopping you in having multiple layers of these, so again, they can become complicated if you make them so. And again, a couple of games that have used these in the past. Okay, so next we are going to be covering Goal-Oriented Action Planner, or GOAP for short. So, unlike state machines and other architectures we'll cover in a few slides, GOAP is actually in charge of creating a plan ahead of time that the NPC will execute at a later point. And it does this by running through a sequence of actions and putting them together at runtime. And that will be our plan. As such, behaviors are not explicitly defined. This means that a designer has not gone in and put together very specific behaviors for the NPCs to execute. Instead, we will be creating modular actions, and the planner will stitch these actions together at runtime, and those actions will make up a plan, and that will be your behavior. It's goal driven, so the NPCs will be trying to accomplish a specific goal, and the point of the plan is to be able to accomplish a very specific goal. And the actions will define how the plan is achieved. So I want to run through a few different concepts of GOP, a bit of terminology. So the first one is world state. And we can think of world state as a set of variables that define the NPC's understanding of the world around them. It can have variables that are static, so things about the world that never change, but it can have things that are very, very specific to the NPC's vision or understanding of the world. We'll be talking a little bit more about this in the next slide. Goals. So again, everything runs back to world state, and the goal and our goals are just trying to pursue a very specific world state. As in, our goals will define certain variables that we want to have changed in the current world state. And our actions are how we go about actually achieving our goals and impacting the state of the world. So, a little more in depth about the world state. This is a data structure that will contain variables about the NPC's knowledge of the world. How you define this structure is up to you in your implementation, because you can store different types of data, or you can have it all being strings and booleans. It really depends on how you want to contain this information. But in essence, it needs to be able to read information that the NPC can access, and the scope will be using to determine from that NPC's point of view, what is the current state of the world. So it can have information that's very specific to the NPC, such as how much ammo it has, inventory information, its health, or not. It's really up to you. You can also store that information in other bits of data. It will very much depend on the design of your game. One important concept when talking about world state is that we will have a working world state while executing a plan, while planning the plan. This is to mean that we start with a starting world state, but to achieve a certain goal, we are going to have to enact certain actions, and those actions will impact a hypothetical world state. And we will be working with that world state to determine if we've achieved our goal. This will make a little bit more sense in a few slides when we run through an example. And some examples of world states might be has weapon, enemy in sight, has an LKP of the player, etc. So goals. They describe desired outcomes, as in which world state variables we want to affect. So for example, a goal might be to kill the player. So we might want to impact the enemy is dead world state variable, for example. Goal prioritization, you will have many different goals in your game, and how you prioritize each goal will define which goals and which plan we will pursue. And some examples of goals might be kill enemies, satisfy hunger, ambush, etc. So, our actions, they are defined as a set of preconditions and effects, and these preconditions are a set of world state variables. So for example, being able to shoot, you might have a precondition to be in a specific range to optimally shoot from. You might have to have a weapon, that weapon might have to be loaded. So these are all preconditions for a shoot action, as an example. And then they have an effect. Again, the shooting action might have the effect of killing the player. Again, all defined by world state variables. Which world state variables is it going to impact? So we're going to walk through an example. And we're going to start off by having a look at 3 goals. As you can see, they all have a priority, and we've decided to pick the kill enemy goal because it has the highest priority. So we want to kill the enemy. And to do that, we're going to have to look at our list of actions and see which ones have the effects that we're looking for. For our goal of kill enemy, we are looking for the enemy is dead effect. And for that, we have two actions that can accomplish this goal. We have the ranged attack action and the melee attack action. As you can see in the effects section, both of them have the enemy is dead equals true. And that's what we want. So our planner is going to have to evaluate both, and we're going to try to create a plan that can kill our enemy. We'll start off with the ranged attack action. And the way this will work is we will look at all of our preconditions and we will determine, are we in a state of the world that satisfies all of our preconditions to be able to use the ranged attack action. So the first one is the has weapon equipped, and we've derived that we do not have a weapon equipped. Okay, so now we're going to have to look again for a list of actions that have the effect to equip a weapon. We found the action equip weapon, which has the effect we're looking for. And so we chain that to our plan. So in order to perform a ranged attack action, we first have to equip a weapon. So we are going to chain the equip action. Our equip weapon also has its own set of preconditions. It must have a weapon. If we don't have a weapon, then we have to get to a state of the world where we will have a weapon. So again, we do the same exercise and we look for a list of actions and search for which ones have the effect we're looking for. And we found the search weapon action. This one has the effect we're looking for. So again, we'll add it to our plan. And we continue from there, because again, our search action has to be a specific precondition. We've determined that we have the knowledge that a weapon can be found at a specific location, and we're not at that location. Therefore, we have to find an action that will get us to that location. And again, we get the go-to action. Luckily, our go-to doesn't have any preconditions, so that's where it would end this chain of actions. But we now got to a point where we found a weapon, we equipped it, and we're ready to shoot, right? Well, no, not quite yet, because we're not quite done with our list of preconditions for our ranged attack action. Next thing to do is look at our weapon loaded. And if our weapon is not loaded, then we need to look for an action that can impact this world state variable. And in this case, we found the reload weapon, which has the effect we're looking for. Cool. But now the reload weapon also has its own set of preconditions. Luckily enough, its preconditions were already being met, so we don't have to go through this exercise. So great. So we'll just look at the next precondition for the ranged attack, which will be the at location, because we need to be able to be at an optimal position to be able to shoot from. So again, we'll use the go-to action that we already used before. And great. So we have a possible plan right now that can achieve the goal of killing our enemy. You'll start by searching for the weapon. We will equip the weapon, reload the weapon. We get to an optimal range, and then we can finally shoot the player. Great. But this was one possible plan. As we saw, there were two actions at the start that satisfied the condition to kill our enemy: the melee attack action and the ranged attack action. Now you would go, you'd pick up the melee attack action and you do the exact same exercise you've just done with the ranged attack action, going through all of its preconditions and finding all the actions that can satisfy them until you get to a final plan with it. Now, you can get to a point where you have to select, okay, which plan will I actually enact? Which chain of actions will I execute to achieve our goals? And this is where we use things like cost. At this point, you might have realized that a lot of what we're doing is a graph transversal exercise. So it's analogous to finding a path in a pathfinding algorithm. So you'd use things like cost and maybe even heuristics, depending on the algorithm you're using, to be able to determine which plan would be the cheapest, analogous to which path would be the cheapest. So a few examples of games that have used GOPE, Fear being the most the one that kind of brought it to popularity, but there were a few games after that that have also used it since. So some of the advantages of GOPE, it provides historical information because you are pre-computing a plan to be executed. You'll just get that historical information for free, which is great for debugging. It's highly systemic. Fear was a great example of this, where a lot of their design was based on the environment and how the NPCs interact with their environment, and less about creating big sequences of behaviors. So because you're just focusing more on the modular actions and you let the planner figure out how to stitch those actions to achieve their goals, it creates a really high level of systemic gameplay. They're quite scalable. When we looked at state machines, adding one state was a bit of a nightmare because you have to go back to every single state and figure out which state, which transitions you need to add to the new state. In here, adding a new action is quite simple. It's just, as long as you're using world state variables that were already present, the planner will suddenly just use that new action if it makes sense to do so. Some things to consider. Why did they just do that? This is something that will leave your designers scratching their heads. Because it's so systemic, you might be wondering sometimes why did they decide to do that at that moment in time. Debugging information will be here, will be your friend here. Have as much of that information as possible. Things like why did it decide to pursue this goal? Why did it reject other goals? Why did it not perform one action over another? So all this information would be really useful to debug these sort of issues. Can it be expensive? In the past, this has been one of the downsides that Cope could have. But you can optimize it. You are dealing with a graph transversal operation, so doing things like reducing the search space will help you here. Delegating processing to different systems so that Cope can become more lightweight will also help. So don't be afraid of the expensive part because there's a lot you can do to optimize it. Okay, so next we're going to cover one of the most common technologies in video games right now, and that is behavior trees. And you might be very familiar with them since they are very used in Unreal. But before we go into specifics, I want to first take a step back and talk about how trees work. So a tree is a hierarchical graph data structure, which is executed from its root node. Now, behavior trees will have only one child from its root node, which will be a composite node. We will cover what that means in a few slides. And the important thing that I want you to get from this is that tree will be transversed top to bottom, left to right. So a few examples of leaf nodes. These will be the nodes that will be executed, and they might be things like go to, send an event, play an animation, etc. So let's say you send an event or whatever node you're executing. You will want it to return some states so that you know how the tree should continue to execute. So the first state we're going to see is success. So that means the node executed, nothing went wrong, it returned as expected, so it returns a success state. Great. But your tree might be running, your node might be running for a few different frames or even seconds or minutes. For example, if you're doing a goto, you might be running it from the point that the NPC starts navigating to the point that it gets to its destination. So in that case, we'll be returning a running state for however long it takes for them to get to its destination. But it can also return a failure. Again, if we look at goto, maybe it found an obstacle in the way. Maybe it didn't even succeed in finding a path in the first place. So it will return a failure state. Okay, we are going to be talking about composite nodes and what these are. So these are nodes that aim to control the execution flow of all of its children. They can be used to group up more complex behaviors. And once a child returns a particular state, it will then decide what it will do. So it can mean that it might go and execute the next child, it might pick a random child, or it might just return back to its parent. It depends on the type of composite node. And we will be talking about different composite nodes right now. So the first one is the selector node. Selector node, it will select a node. So it will execute until it finds a child node that returns success. So in this case, we have an example. We have three nodes, hide, patrol, and investigate. We run through the hide node, it fails. So we'll try to run the next child from left to right. It will be running the patrol, and it succeeded. Because it found a success state, it will then return its success state. Because selector node will only run until it finds a success state or until all of its children fail, and then it will return a failure status. The next type of composite node is sequence nodes. These will run all of its children until either all of them succeed or one of them fails. So in this example, we run a goto, it will return a running status, it will then succeed. We'll use the smart object, which again returns a running status, it will succeed, and it will play, in the next node, it will play sound, and then the whole sequence succeeds because all of its children succeeded. However, if the goto had failed, then the whole sequence will fail. And the same thing for all of its children. All it takes is for one of its children to fail for all of the sequence to fail. Parallel nodes, as the name indicates, it allows you to run multiple nodes at the same time. This doesn't necessarily mean that it's multi-threaded, it just means that they will be executed in the same frame, just one after the other. And you can have different rules to determine how you might want to break out of the parallel node, what it means to fail. For example, if play sound plays 3 times, then succeeds in this example. The logic's up to you. So, decorator nodes. So this is another type of, we've just covered composite nodes. Now we're going to look at a different type of node, which is decorator nodes. Unlike composite nodes, decorator nodes can only have a single child because its aim is to impact the status result or the execution flow of its single child. And a few examples of this, we have the inverter decorator. This just inverts the result status of its child node. So if it's success, it will return failure and vice versa. The repeater decorator, it will repeat the child nodes predetermined amount of times. And the conditional decorator will only run its child if a certain condition is true. And finally, the success decorator, it will just return, it's fine. It always returns success, don't worry about it. And putting it all together with some of the decorators and composite nodes we looked at, here's some what a behavior tree might look like. Again, very simplified. So what games use it? Quite a lot of them. It's an incredibly popular technique nowadays, but here's a couple of examples of games that have used it. Some of the advantages, you make use of modular reusable actions. So all of your task nodes, your leaf nodes, you can just reuse them across different trees. You can even reuse your trees and use them as subtrees. So it can be quite a modular architecture. It's quite visual, especially if you have a good editor. So it can be easy to follow the logic depending on your implementation. And anyone can use them once you've set up all of these types of nodes and your leaf nodes. Then it's very easy to give it to a designer, and they can go around and set up their tree and have all sorts of different behaviors from these modular actions. Some things to consider is behavior trees are decision-making. It's a decision-making system, so that is what it's good at. It's not great at transitioning between behaviors. If to do that, you'd want a state machine. So it's good to let your decision tree do what it's good at. And that means not putting too much logic on your tree. The lighter weight, the more information and processing you can delegate to specialized systems, the more your behavior tree can focus on the things that it's good at. Okay, so next architecture we're going to cover is utility systems. And utility systems aims at scoring different actions so that the NPCs can select which action to execute over one another. And the way that we do that is we score each action, and we calculate a score based on utility functions. So we're going to run through a very simple example. We have a game with an NPC, and this NPC can do 3 actions. It can eat, drink, or pet a dog. So we're going to look at each individual action, and we're going to try to calculate a score. So we have our eat action, and we're going to say, okay, we're going to look at our value of hunger. And however, how much hungry we have, that will be correlated to our utility score. So our hunger right now is 0.3, so our eat score will be 0.3. Great. That's our utility score. However, not all foods are made the same. Maybe I am not that hungry for banana, but I would completely devour a cupcake right now. So To model it more realistically, maybe we'll want to add appetite as a parameter to our utility score calculation. So we'll do just that. We'll take these two values, we'll average them out, and we'll get the score out of them. But maybe in a real world scenario, we shouldn't just let appetite be have the same weight as hunger. You know, hunger relates to our survival. So maybe we'll add a weight and we'll say that we'll want hunger to constitute 70% of our score, while appetite only 30%. And now we'll get a better result that more realistically portrays what we're after. Next, we're going to have a look at our drink action. Now, as humans, we really need to drink or we die. So we're going to do a few things to make sure that our NPCs really prioritize drinking. One of them is making sure that they always have the option to drink, and that is by giving it a utility score that starts at 0.2 instead of 0. This means that as long as there are other actions that have a score below 0.2, we will still go for a drink even if we are not that thirsty, just to top up. The other thing that we'll do is we'll want to cap out our utility score at 1 whenever we reach 0.7 value of thirst. This is to give us a buffer between 0.7 and 1 of thirst, where potentially the NPC could die of thirst while trying to get to its drink. In this example, we've used two functions and we've calculated the minimum of the two functions to reach the utility score that we're after. So we've calculated how the eat action, we've calculated the drink action, but we still have to calculate how to pet a dog. And how do we do that? It turns out it's not that difficult. NPC would rather just pet the dog. Doesn't need to drink, doesn't need to eat, just pet the dog. Right, a few examples of utility functions. You can go as crazy as you want with these. If you are going to implement this and you don't have a curve editor, highly recommend creating one for your designers so that they can create whatever functions they want for different actions. And a few examples of games that have used it, Sims being one of the most popular ones. So, some advantages. It's great complementing other systems. For example, in an action in GOP, you might give a score of an action based on a utility calculation. You might have a conditional node in a behavior tree where the conditional is based on a value that was again calculated by a utility function. So it incorporates really well with other architectures. Data-driven, you can pack a lot of data into the environment with these. The Sims is a great example of this, where they've shipped whole DLCs with just data because their systems were already set up to work with these functions. So they've just packed that data into their environment. And highly systemic, again, because it can work really well with things like smart objects and other information you can pop in the environment. It can create some really high level of systemic gameplay. Some things to consider. Tuning, your designers will spend a lot of time tuning these utility functions so that the NPCs can behave the way they want them to, and trying to chase edge cases. Decision oscillation, you might come to a situation where an NPC might be oscillating between a behavior and another based on numerical values that are quite close to each other. So you might want to enact a bit of inertia into those. So things like a cooldown, making sure that the behavior, a certain action is not executed straight after it just executed, for example. There's different things you can do to solve this. Okay, very quickly, on our next section, I wanted to cover some of the tools that will be really useful for you to debug your NPCs. And I'll be using a lot of examples from Unreal because they have a few good tools already set up in there. First one, a visualizer. Things like Sense Visualizer to visualize your vision cones, events, stimuli, auditory stimuli. Being able to perceive all these things in the world is really, really going to help you. Storing chronological data. Again, this is a great tool that Unreal has called the Visual Logger tool. It essentially allows you to store a bunch of debug logs and even debug shapes in a chronological fashion. This means that you can then replay and see which state the NPC was in at a very particular moment in time. So yeah, storing positional information, its state information, what animations they were playing, all of that will be really, really useful when you're debugging your NPCs. And finally, if you are, whatever architecture that you choose to employ, having a really good editor that your designers can use will go a long way. And if that could double down as a debugger as well, as an example, the behavior tree editor that allows you to both create a behavior tree and debug it, it's really, really useful. Okay, so which choice is the right one for your project? Well, there's no silver bullet here. It will honestly depend on the design of your project and what behaviors you're trying to model. And if you're aiming for having very, very simple behaviors, state machines are a great tool to use if you can contain them. If you want to create high-level systemic NPCs, maybe GOP is the right choice for you because you can just have the action planner make at runtime create those plans. If you want your designers to have a greater impact on how your NPCs act at very specific moments in time, a behavior tree is a great tool to allow you to do that. But also, why not try a mix of things? We've talked about how utility systems can be used in conjunction with other systems, but also you can have, for example, a state machine where one of the states is a behavior tree, or a behavior tree where one of the leaf nodes might be a state machine. It's very easy to mix and match these systems, so don't be afraid to experiment. Well, thank you so much for listening to this talk. If you have any questions, I will be here after the talk. And please don't forget to check out the State of AI in Unreal tomorrow. Thank you so much.
Brilliant stuff. Thank you so much for that, Ricardo. Thank you for everyone jumping into the chat area. I'm sure you enjoyed that as much as I did. I found it super interesting. So show some appreciation if you haven't already in that chat area. And the Q&A is also still open as well. So if you do have any questions, pop them into that Q&A area. We do have quite a few come through. So don't worry if you're unable to get your questions answered this time. They will be posted onto the Dojo page. Which leads me to answer the first question, which was, is this being recorded? Will we have access to it? Yes, these will arrive in the SDC vault over on Dojo, so you'll be able to rewatch these back to your heart's content. Ricardo, thank you so much for doing that presentation for us. I was really looking forward to watching it and understanding how, first of all, how NPC works. I'm afraid I'm a little bit ignorant to how much work goes into some of these things, and you almost made it sound like it was quite easy. So that was brilliant. Yeah, a lot of claps coming in through chat as well. Brilliant and really concise. Yeah, absolutely. As I said, you explained it in such a way that even I understood it as well. I don't do any kind of coding whatsoever. What I want to do is, first of all, let you say hi to everyone, but also I want to move across to the questions. But Ricardo, how did it feel to watch yourself back?
Hi, everyone. Thank you so much for watching. Yeah, not too many blunders, which is good. So yeah, pretty happy about that. And thank you for all the questions. We have quite a few.
Yeah, they're flying in. Brilliant stuff. And as I said, just to repeat before, any questions we don't get through within the next 10 minutes, we will fire over onto Dojo and get them answered for you. I'm going to go into the first one. It was the very first question that came in, which was from Yannick, and it was, in GOP action definitions, do you require that the implementer tags the action up manually with the preconditions and effects, or is there a system where you can determine it via code in an offline step?
Yeah, so usually you would have either a programmer or a designer set up those tags. It will depend on your implementation. If your system is very data-driven, you can expose that to designers so they can do it themselves. If you're finding that you have a lot of world state variables or a lot of tags that you can actually change and you have a lot of actions and this becomes quite cumbersome during development, there's nothing stopping you from adding things like templates that will automatically set up a bunch of these tags just to give you a bit of a starting point and cutting down on some of the boilerplate. So it's up to you. Usually you would have to manually set these up, but if it becomes cumbersome, then you can look into an automated solution for it.
Fantastic. Thank you for answering that. The next question that comes is from Kyle and is how performant is FSM slash HFSM versus GOP?
So it will depend obviously on how complicated your state machines versus how complicated your search space is for GOP. In general, GOP is pre-computing. It is a graph traversal operation. So the higher your search space is, the more nodes you'll have to visit, the more expensive it tends to be. So usually it would be more expensive. But then if you look at your number of states and how many possible transitions you might have, chances are, state machines will be cheaper, but it will depend on what you have. It's not usually a reason to select between either or, though. You would be mostly looking at how easy it would be to work with either and which one fits better design of your project. If it's quite simple stuff that you're trying to model, you can get away with a state machine. If you're looking for highly systemic stuff, then GOP would be a better choice.
Brilliant stuff. Thank you again. I just wanted to read out a comment from Faye, just as we're going through between the questions. It says, I've always heard people talk about behavior trees, but never knew what they were. Thanks. It was really, really interesting. Thank you, Faye. I was struggling to point to words exactly what I was thinking as well. I'd heard of behavior trees, never knew what they were. And you dissected it and you were concise and explained it really, really well. Thank you. I'm going to move on to the next question. It's a bit of a big one. I'll do my best to read it out. And make sense of it, or make it make sense. Is it ever sensible to combine GOP for high-level decision making with state machines for the complex / rapid logic? For example, once you have satisfied the precognition to attack a player, rather than going straight to attack, you transition into a state machine which controls the various states within the attack: hide, shoot, run. Or can you achieve the same effect / better result with GOP alone? Thanks. That's from Joe.
Yeah, you can absolutely mix and match the architectures. That was one of the last points of the talk, was you can choose to, as you gave a good example. I think what you've suggested is a really good way of doing it, which is to have GOP create a high-level plan and then let other systems handle the more player-centric side of it, because they will do it better. You could, for example, even run a behavior tree. You gave the example of state machine. It could be, for example, a behavior tree. One of the, you're pre-computing your plan with GOP. So once you get to either go to or attack or whatever, then there's nothing stopping you from, once you get to that execution phase, to just let whatever you want to run. It could be a state machine, could be a behavior tree. I do think personally that GOP is good at the planning side of it, but letting something that maybe a designer can more easily handle, like a behavior tree, would give you better results on the execution phase of it. But again, highly dependent on your game and what your designers are also more familiar with doing.
Great stuff, and that's brilliant. I'm going to transition on that note, transition to another question from Kyle, which is one system better or more suited for certain genre of games?
It will, again, yes, it will depend on the type of game you're making. If you want something more systemic, for things that you want your NPCs to be highly reactive of the environment around them, GOP is really good for that. If you want your designers to be able to handcraft more the experiences and be able to do very scripted sequences of behaviors, a behavior tree would be a better, it would do a better job at it. An interesting point of this is that GOP is just an extended behavior tree. What I mean by this is that every plan could be turned into a behavior tree, but you're not creating that behavior tree manually. GOP allows you to have essentially a giant behavior tree that chances are you wouldn't be during development, you wouldn't have the resource and you wouldn't be able to do it yourself. So that's the good thing about Cope. It allows you for the possibilities that you didn't think of. And it was actually one of the cool points about when Fear came out and they were giving their talk and publishing their paper, said the amount of emergent behavior that came out of it that they didn't realize would happen just because the planner is teaching these actions at runtime.
Right, got you. Okay, and I think this next question is along the same lines. It's from Angelo, and it says, would it be useful to combine Go with machine learning? Would that bring any benefits for some type of games?
I did consider if I wanted to make a very quick one on machine learning on this talk, but there was not a lot of time. So machine learning can try to solve some of these problems as well, but the big problem with machine learning is it requires a whole lot of data for it to model the problems you're trying to solve. So GOP is trying to rationalize information, giving some inputs. Let's try to get to our end state. I wouldn't see, I personally wouldn't see the benefit of putting the two together. But you could try to use machine learning to solve some of the decision-making aspects of NPC decision-making, but it would just be very difficult because of the amount of data that you'd need to do. Which is why we haven't really used it that much in this side of video games. We have used it in other parts, like algorithms for motion matching, where you have a lot of animation data and you'd be able to use machine learning to get a better prediction algorithm of which animation to use, for example. But I haven't seen it used for decision making yet.
Brilliant stuff. Thank you for that. I got a question from Yannick. It says, in your experience with GOP, how frequently are your agents having to replan?
So there will be specific parts of the game where you will kind of want a kind of like an override, a replan right now. For example, if the NPC gets hit, so during a hit reaction, that would be a good time to do a replan. Because it would make sense, right? If the NPC gets hit by a bullet, chances are that he's no longer interested in going to grab that drink. He's probably more interested in running away or shooting the player back. But aside from that, you can obviously do incremental, like every other frame or every 200 milliseconds or whatever. You can do timely replans, for example. It's something that you can balance. You can start with a certain frequency rate of replanning and then seeing how far you can get with that. And then obviously if you have performance issues, then you can reduce and just play around with those values.
I hope that answers your question, Yannick. Yeah, it sounded like a proper solution. Right, we are running out of time, Ricardo, so I am actually going to switch to a question that I've been saving, and it's, do you have reading materials or a reading material or tutorials perhaps on YouTube for these methods?
My go-to is the Game AI Pro, I think .com. Game AI Pro is a really good book series. They've published quite a few volumes over the years, and now they published everything on all the articles on their website. Really, really good to see what people in the industry are doing. These are written by real industry professionals that have published games. A lot of the times they will use the examples from the games that they've published. So really, really good wealth of information there. I really enjoy reading through those articles. So that's my number one recommendation for Game AI.
Brilliant stuff. Thank you very much, Rico. You heard it here. That number one recommendation if you want to learn any of this stuff that Ricardo has covered today. Right, that is all we have time for. Yes, GCC Vault is also available as well for any information. Right, that is all we have time for today in this session. Again, thank you so much, Ricardo, for doing our presentation for us, for answering everybody's questions as well. I will reiterate anything that we didn't answer during this session, we will get across to Dojo. So look out for those when they're published and have a read through them. For now, though, that is it for this session. Again, thank you very much, Ricardo. Really appreciate you and spending some time of putting all that information together, dissecting it in such a concise way as well. For now, though, it is over. And
Can we please also get some love for Richard for hosting this as well? Thank you very much.
Appreciate you, man. Brilliant stuff. That's all we got time for today. Look out for the video over on Dojo in the SDC Vault. For now, though, we'll end it there, and we'll see you again in the near future. Enjoy the rest of your SDC show if we don't see you again. Bye for now.
Thank you.